I came across this book about Maxwell's equations. It's a really detailed guide about a few of the most important equations in physics and engineering. It starts from the really basics and it focuses on those four equations. It's not like any engineering book that just goes directly to the point of where we use those equations. It starts by Gauss's law for electric fields, and then magnetic fields, Faraday's law, and then Ampere-Maxwell law. And then it will give us a quick look about from Maxwell's equations to the wave equation. So it will be a really great guide if you are in engineering or physics. You will study electromagnetic waves, for example. Let's start by the first chapter. In Maxwell's equations, you'll encounter two kinds of electric fields: the electrostatic field by electric charges and the induced electric field by changing magnetic field. So there will be just a charge and it will have some electric field around it. And then the other type of field, it's an induced electric field produced by changing magnetic field. Gauss's law for electric fields deals with the electrostatic field. So first we'll see the electrostatic field. You'll find this law to be a very powerful tool because it relates the spatial behavior of electrostatic field to the charge distribution that produces it. So a quick look at the equation here, we see that it relates the electric field by the charges. There are many ways to express Gauss's law, and although notation differs among textbooks, the integral form is generally written like that. It's like that, and we'll see it here in a second in more details. The left side of this equation is no more than a mathematical description of the electric flux, the number of electric field lines passing through a closed surface S. So as we will see later, we're going to integrate over a specific surface to find the electric flux coming or going into it. Whereas the right side is the total amount of charge contained within that surface divided by a constant called the permittivity of free space. So this is the permittivity of free space. It's just a constant, and then other materials have permittivities too. If you're not sure of the exact meaning of field line or electric flux, don't worry, you can read about these concepts in detail later in this chapter. You'll also find several examples showing you how to use Gauss's law to solve problems involving the electrostatic field. For starters, making sure you grasp the main idea of Gauss's law. Electric charge produces an electric field, and the flux of that field passing through any closed surface is proportional to the total charge contained within that surface. So if we have more charges, we have more fields. So if we have a surface, for example, it has only one charge, it will have way less field if we have another surface that has way more charges than it. Also depends on the sign of the charge, whether it's positive or negative, the field is coming in, coming out, or the positive and negative charges are equal, so the net is zero. In other words, if you have a real or imaginary closed surface of any size and shape and there is no charge inside the surface, the electric flux through the surface must be zero. Of course, obviously, as there are no charges, so where will the field come from? If you were to place some positive charge anywhere inside the surface, the electric flux through the surface would be positive. If you then added an equal amount of negative charge inside the surface, making the total enclosed charge zero, the flux again will be zero. Remember that it's the net charge enclosed by the surface that matters in Gauss's law. So that's why we integrate over a surface. And we're seeing here that we're concerned with the charge enclosed. To help you understand the meaning of each symbol in the integral of Gauss's law, for electric fields, here's an expanded view. So let's see one by one. First, the integration part. It says that we're going to integrate over a surface. Okay, we'll see what that means later. Electric field is a vector, and then we're going to dot product. We'll see that what is a dot product later. We're going to talk about the unit vector, and we're going to integrate over the surface. Whatever that integration is, it equals the charge enclosed over the permittivity of free space. How is Gauss's law useful? There are two basic types of problems that you can solve using this equation. The first one is if you have electric field and you want the charges, or you have the charges and you want electric field or flux. The best thing about Gauss's law is that for certain highly symmetric distributions of charges, you can use it to find the electric field itself. So we could either find the flux or the electric field, rather than just electric flux over a surface. Although the integral form of Gauss's law may look complicated, it's completely understandable if you consider the terms one at a time. That's exactly what you'll find in the following sections, starting with the electric field. To understand Gauss's law, you first have to understand the concept of the electric field. In some physics and engineering books, no direct definition of the electric field is given. Instead, you'll find a statement that an electric field is said to exist at any region which electrical forces act. But what exactly is an electric field? This question has deep philosophical significance, but it's not easy to answer. It was Michael Faraday who first referred to an electric field of force, and James Clerk Maxwell identified that field as the space around an electrified object, a space in which electric forces act. So they both work together to find a specific definition for the electric field. The common thread running through most attempts to define the electric field is that fields and forces are closely related. So here is a very pragmatic definition. An electric field is the electrical forces per unit charge exerted on a charged object. So here is a definition of the electric field is that it's a force exerted on charges. Force per unit charge exerted on a charged object. Although philosophers debate the true meaning of the electric field, you can solve many practical problems by thinking of electric field at any location as the number of newtons of electric force exerted on each column of charge at that location. Thus, the electric field may be defined by that relation. It says that you could think about electric fields as forces, so the newtons exerted by columns, so force exerted on charges, okay? Where force is the electrical force on a small charge. This definition makes clear two important characteristics of the electric field. E is a vector quantity with magnitude directly proportional to force. Okay, so obviously it's directly proportional, and it's also a vector, so it has a direction. Its direction is given by the direction of a force on a positive dust charge. Electric field has units of newtons per column. It's visible in this equation where force's unit is newtons and the charge's units are columns, which are the same as volts per meter, because volts is newtons per times meters of column, so newtons per column divided by meter to remove this meter and be newtons per column, which is the unit of the electric field. In applying Gauss's law, it's often helpful to be able to visualize the electric field in the vicinity of a charged object. The most common approach to constructing a visual representation of an electric field are to use either arrows or field lines. So as we will see in a second, field could be represented by arrows or just field lines. Okay, here they're using arrows to represent the electric field, where the length of the arrow says how strong is the electric field. And when using lines, is the spacing of the lines that tells you the field strength, with closer lines signifying a stronger field. When you look at a drawing of electric field lines or arrows, be sure to remember that the field exists between the lines as well. So the drawing is just a representation, and of course, there are fields in between those drawings. Examples of several electric fields relevant to the application of Gauss's law are shown in figure 1.1. So this figure, we have a positive charge and electric field is coming out of it, negative charges with electric fields going into it. So as we can conclude that electric field starts from a positive charge and ends in a negative charge, which is visible in here. So here is a positive charge, the electric field starts from it, and a negative charge here that electric field ends in it. There is also an infinite line of positive charges, infinite plane of negative charge, and positively charged conducting sphere. Here are a few rules of thumb that will help you visualize and sketch the electric field produced by charges. Electric field lines must originate on positive, that's what we were just saying, so it starts on a positive charge and terminates on negative charge. The electric field at any point is the vector sum, so electric field is a vector, so we have to take direction into consideration with the magnitude. Electric field line can never cross. So if an electric field crosses with one another, we could say at that exact point, is the electric field coming this way or this way? This can't happen. So electric field at any point is just their sum. We'll see which one is stronger and whatsoever, and then represent it that way. So it's the vector sum, so we take direction into consideration. Those are some formulas for electric fields for different objects, like point charge, conducting sphere, insulating sphere, infinite line charge, infinite flat plane with surface charge density equals sigma. Okay, so let's complete the sentence. Okay, so it was just saying us that vector sum of the individual fields and the electric field lines always point in the single direction of the total field. Okay, electric field lines are always perpendicular to the surface of a conductor in equilibrium. So we could see that here. Here is the surface, and the electric field lines are just perpendicular on it. Equations for the electric field in the vicinity of some simple objects may be found in table 1.1. Okay, so exactly what does the electric field in Gauss's law represent? It represents that total electric field at each point on the surface under consideration. So for example, we took this surface, it just takes into consideration the electric field at every point. The surface may be real or imaginary, as you'll see when you read about the meaning of the surface integral in Gauss's law. So we'll see surface integral in just a second. But first, you should consider the dot product and unit normal that appears inside the integral. So this book just covers everything. We'll go through everything and we'll talk about the basics. First, it starts with the dot product. When you're dealing with an equation that contains a multiplication symbol, a circle, or a cross, it's a good idea to examine the terms on the both sides of the symbol. If they're printed in bold font or wearing a vector hat, so this is a vector and this is also a vector. And if they're bold, so here is just a normal scalar x, but if it was like in a bolder way, you'll know it's a vector. The equation involves vector multiplication, and there are several different ways to multiply vectors. In Gauss's law, the circle between electric field and the unit normal vector represents the dot product or scalar product, as its result is just a scalar number. Okay, in Gauss's law, the circle between them, so it's just saying they're a dot product together. If you know the Cartesian components of each vector, you can compute this as this. So if we have electric field that has an x component, a y component, a z component, and then the other vector has some components, the dot product will be just this component times this component plus this component times this component plus this component times this component. Okay, and it will result in just one singular scalar number. Another way to write the dot product is getting the magnitude of the first time, the second time, cosine the angle between them, where A and magnitude A and magnitude B represent the magnitude length of the vectors. Notice that the dot product between two vectors gives a scalar result. Okay, so this is what I was just saying. To grasp the physical significance of the dot product, consider vectors A and B that differ in direction by angle theta. So here is an example for us. We have this vector that has a specific direction and this vector that has another specific direction. So it's not just normal multiplication. We could say 5 times 3 equals 15. No, it's not like that, as each of one of them has a specific direction. They're vectors, not just scalar numbers. So let's see how the dot product is graphically represented. Okay, for these vectors, the projection of A onto B is A cosine theta. So if we have some projection of A on B, it will be A cosine theta. Multiplying this projection by the length of B gives AB cosine theta. Thus, the dot product A dot product B represents the projection of A onto the direction of B multiplied by the length of B. The usefulness of this operation, Gauss's law, will become clear once you understand the meaning of the vector n. We'll talk about that in just a couple minutes. You could also say it's the projection of B on A times the magnitude of A. This is what they're saying in here. So here it comes, the unit normal vector. The concept of the unit normal vector is straightforward. At any point on a surface, imagine a vector with length of 1 pointing in the direction perpendicular to the surface. So if we have a specific surface like this one, imagine the normal vector to be like that. It's just a normal component perpendicular on the surface with a magnitude of 1, length of 1 pointing in the direction perpendicular to the surface. Such a vector labeled n hat, okay, is called a unit vector because its length is unity, and normal because it's perpendicular to the surface. The unit normal for a planar surface is shown in figure 1.3a. So is the unit normal component pointing in this way or the other way? Here it says we could have chosen it to be in the opposite direction. There is no fundamental difference between one side of an open surface and the other, and it's telling us what's the definition of an open surface. It's just saying that we could go from one side to the other side without crossing the surface, without going through the surface. For a closed surface, defined as a surface that divides the space into an inside and outside, so there's some outside space in here and there's inside space. There are no choices, whereas the direction of the normal vector is defined as the direction going out of our surface. So it just says that it's pointing outward, and this is the convention. Notice that the unit normal vector at Earth's north and south pole will point in opposite direction if Earth was a perfect sphere. You should be aware that some authors use the notation dA rather than n hat dA. So in some books you'll find it that way, where it just defines as this thing as a vector, and here it's saying that n hat times dA. So this is a vector of magnitude dA, and here we're using n hat just to tell us where we're pointing and multiplied by dA, so it's just the same thing. In that notation, the unit normal vector is incorporated into the vector area element dA, which has a magnitude equal to the area dA and direction along the surface normal. So they have the same direction, the same magnitude, just different notations. Thus, dA vector and hat dA serve the same purpose. Next, component of E normal to a surface. So we saw what's an electric field, we saw the unit normal, and we saw the meaning of the dot product. Now let's discuss this as a whole. If you understand the dot product and unit normal vector, the meaning of E dot n hat should be clear. This expression represents the component of the electric field vector that is perpendicular to the surface under consideration. So why is it saying perpendicular to the surface? So this is our surface, for example, and points this way, and there is some electric field this way. So dot product of E dot product with n will give us the component of the electric field pointing in the direction of n, and n is perpendicular to the surface. That's why it's telling us that the product will give us the electric field that's perpendicular to the surface. If the reasoning behind the statement isn't apparent to you, recall that the dot product between two vectors, such as E and n, is simply the projection of the first onto the second multiplied by the length of the second. Also recall, by definition, the length of the unit normal is 1, so that their dot product is just the magnitude of electric field times the cosine of the angle between them. This is the component of electric field vector perpendicular to the surface, as illustrated in figure 1.4. So this is what I was just saying. There's a normal component to our surface, and there's some electric field, so the dot product will give us the electric field that is in this direction. And then it goes on telling us what if the angle is 90 and what if the angle is 0. So let's see if the angle between them is 90. Let me point in the other direction. If it's 90, it's perpendicular to n, which means the electric field is parallel to the surface. So this is our surface, the electric field is parallel to it and perpendicular. So there is no component of the electric field on n. The dot product will be 0. What if it's the angle between them is 0? That means that they have the same direction, and their dot product will be just the magnitude of electric field, as all of the electric field would be on n. In this case, the component of electric field perpendicular to the surface is the entire length of electric field. The importance of the electric field component normal to the surface will become clear when you consider electric flux. So it's telling us that it will have a significance later. To do that, you should make sure you understand the meaning of the surface integral and Gauss's law, and that we'll see next. So our next part is talking about the surface integral. Okay, so the left part, if you remember, was the surface integral of E dot product and dA. So we saw that part, and now we'll talk about the integration meaning. Many equations in physics and engineering, Gauss's law among them, involve the area integral of a scalar function or a vector field over a specified surface. This type of integral is also called surface integral. The time you spend understanding this important mathematical operation will be repaid many times over when you work problems in mechanics, fluid dynamics, electricity, and magnetism. So it is just an important math concept you should know. The meaning of the surface integral could be understood by considering thin surface. So we have, let's just talk about this surface. So it's telling us if we have a very thin surface, such as shown in this figure, imagine that the area density, the mass per unit area. So each part has a specific mass. Okay, so it's telling us that the mass per unit area is just changing, varies with x and y. So going this way, the mass per unit area changes, and going this way, it changes. So we couldn't just find the total mass by multiplying the mass by the total area, because it's changing. You can do this. So it's telling us to find the total mass. You can do this by dividing the surface into two-dimensional segments, over each of which the area density is approximately constant. So we're going to divide it to very, very small parts, where each small part of that, we could approximately say that the mass per unit area will be constant. For individual segments with area density sigma and area dA, the mass of each segment is sigma dA. So we'll just multiply the mass per area times the areas, which will give us the mass for that part. And the mass of the entire surface of n segments is given by this summation. So we'll just sum the mass per unit area times the area, and then we'll just add it all together to find the total mass. As you can imagine, the smaller you make the area segments, the closer this gets to the true mass, since your approximation of constant sigma is more accurate. So if we made those areas smaller and smaller, the concept of the approximation of saying that this specific area is the mass per unit area is constant will be more accurate. So it's telling us as area approaches 0 and n approaches infinity, the summation becomes an integration. This is the area integral of the scalar function sigma xy over the surface. It is simply a way of adding up the contributions of little pieces of a function, the density in this case, to find a total quantity. To understand the integral form of Gauss's law, it's necessary to extend the concept of the surface integral to vector fields, and that's the subject of the next section. So here it was just talking about the surface integral in general, and then here it will tell us about a vector field. In Gauss's law, the surface integral is applied not to a scalar function, such as the density. So here we were talking about the density, but in our formula, the electric field is a vector. So we're going to talk about vector field. What's a vector field? As the name suggests, it's a vector field is distribution of quantities in space, a field. So we have some space and it has some quantities. Each one of them has both magnitude and direction. So imagine we have like a certain space and it has a lot of quantities, each having a magnitude and direction. And that's a vector field. So each one is a vector. So where is the distribution of temperature in a room? An example of a scalar field. So temperature doesn't have a direction. The speed and direction of the flow of fluid at each point in a stream is an example of a vector field. So if we have some liquid, for example, liquid flowing this way is different than liquid flowing this way. So direction matters. The analogy of fluid flow is very helpful to understand the meaning of the flux of a vector field, even when the vector field is static and nothing is actually flowing. So it's just an analogy to help us, but nothing is actually flowing. You can think of the flux of a vector field over a surface as the amount of that field that flows through the surface. So we could imagine that the electric field is the amount of flux that flows or just passes through the surface. In the simplest case of a uniform field and a surface S perpendicular to the direction of the field, the flux is defined as the product of the field magnitude and the area of the surface. So for a specific area, to be able to find how much flux is passing, we'll multiply the magnitude of that times the total area to find the total flux. This case is shown in figure 1.6a. So they were just perpendicular to each other. What if they weren't perpendicular? If the vector field is uniform but is not perpendicular to the surface, as in figure 1.6b, the flux may be determined simply by finding the component of A perpendicular to the surface. So we'll just perform dot product as we learned from a couple of minutes ago. So we'll first get the perpendicular component and then multiply by the surface area. While uniform fields and flat surfaces are helpful in understanding the concept of flux, many E&M problems involve non-uniform fields and curved surfaces. To work those kinds of problems, you'll need to understand how to extend the concept of surface integral to vector fields. Consider the curved surface and vector field A shown in figure 1.7a. So we have some curved surface and a vector field. It's very hard to tell, it's very hard to just say, or we couldn't just say that it's a surface and there's some field passing perpendicular to it. Imagine that A represents the flow of a real fluid and S is a porous membrane. Later, you'll see that this applies to the flux of an electric field through a surface that may be real or purely imaginary. Before proceeding, you should think for a moment about how you might go about finding the rate of flow of material through surface S. You can define the rate of flow in a few different ways, but it will help to frame the question as how many particles pass the membrane at each second. So for the purpose of understanding, we will imagine we have a specific surface. It's porous, so liquid could just flow inside of it, and we'll use it to be able to understand as some kind of analogy. And then we will need to find the rate of flow, so how many particles passes through this membrane each second. So electric field is not actually a liquid, but this is a way for the book to teach us and help make the idea closer to our minds. To answer this question, define A as the number density of the fluid. So A is just particles per cubic meter times the velocity of the flow, meters per second. So particles per cubic meter times what? Meters per second. That will give us particles per meter squared times second. As a product of the number density, a scalar, and the velocity, a vector, A must be a vector in the same direction as the velocity, with units of particles per square meter per second. Since you're trying to find the number of particles per second passing through the surface, dimensional analysis suggests that you multiply A by the area of the surface. So we have particles per area times second. We'll just multiply times the area to find the particles per second, find the rate of flow. But look again at figure 1.7a. at this figure, the different lengths of arrows are meant to suggest that the flow of a material is not spatially uniform, meaning that the speed may be higher or lower at various locations within the flow. This fact alone would mean that material flows through some portions of the surface at a higher rate than other portions, but you must also consider the angle of the surface to the direction of flow. Any portion of the surface lying precisely along the direction of the flow will necessarily have 0 particles per second. So if we have surface that way and just something is flowing parallel to it, we'll just have 0 particles flowing actually in the surface. Since the flow lines must penetrate the surface to carry particles from one side to the other. Thus, you must be concerned not only with the speed of flow and the area of each portion of the membrane, but also the component of the flow perpendicular to the surface. Of course, you know how to find the component of A perpendicular to the surface simply from the dot product of A and N. We learned that the unit normal to the surface, it was just saying us that N is the unit normal to the surface, but since the surface is curved, the direction of N depends on which part of the surface you're considering. So if we have a surface like that, here it will be like that, here it will be like that, here it will be like that. So it depends on which part we're considering. To deal with the different N and A at each location, divide the surface into small segments as shown in figure 1.7b. So here it divided the surface to very small segments. If you make these segments sufficiently small, you can assume that both N and A are constant over each segment. Let Ni represent the unit normal for the ith segment of area dAi. The flow through the segment I as Ai, the product Ni times dAi, and the total is flow through entire surface. Here we find the components parallel to the unit vector, and then we multiply by dA and then sum everything to find the total flow. It should come as no surprise that if we now let the sides of each segment shrink to 0, the summation becomes an integration. That's what we just said like 2 minutes ago. For a closed surface, the integral sign includes a circle just to tell us that it's a closed surface, not an open one. So this is an open surface. We could go from one side to the other, but this is a closed surface. There's inside and outside. This flows the particle flux through a closed surface S, and the similarity to the left side of Gauss's law is striking. You have only to replace the vector field A with the electric field E to make the expression identical. So this is the left part of Gauss's law. We're becoming closer step by step. The electric flux through a closed surface. On the basis of the results of the previous section, you should understand that the flux of a vector field E through surface S can be determined using the following equations. The flux is the electric field times the surface area. To find the component in the direction we want, we'll dot product and then multiply times the surface area. And because it's not uniform, we will integrate. So as we said from a few minutes, we're going to divide it into very small segments and then sum them. And when we make it very small and n tends to infinity, it just turns into an integration. Also, the angles change, so that's why we resorted to integration. These relations indicate that electric flux is a scalar quantity and has units of electric field times area, or Vm. But does the analogy used in the previous section mean that the electric flux should be thought of as a flow of particles, and that the electric field is the product of a density and a velocity? The answer to this question is absolutely not. Remember that when you employ a physical analogy, it's just an analogy to make it closer. You're hoping to learn something about the relationships between quantities, not about the quantities themselves. So you can find the electric flux by integrating the normal components of the electric field over a surface, but you should not think of electric flux as the physical movement of particles. And that's what we said before explaining that part. How should you think of electric flux? One helpful approach follows directly from the use of field lines to represent the electric field. Recall that in such representations, the strength of the electric field at any point is indicated by the spacing of the field lines at that location. More specifically, the electric field strength can be considered to be proportional to the density of field lines, the number of field lines per square meter, in a plane perpendicular to the field at the point under consideration. Integrating the density over the entire surface gives the number of field lines penetrating the surface, and that is exactly what the expression for electric flux gives. Thus, another way to define electric flux is number of field lines penetrating surface. So it was shown in that drawing up here that we could think about flux in some sort. There are two things you have to keep in mind when you think of electric flux as the number of electric field lines penetrating a surface. The first is that field lines are only convenient representation of electric fields, which is actually continuous in space. So as we said earlier, if we represent field in this way, there is also field in between them. Field is continuous and it is just a representation. So it's telling us to keep that in mind. And also the second thing, the number of field lines you choose to draw for a given field is up to you. So as long as you maintain consistency between fields of different strength. So here, for example, saying they're close to each other, so it's strong in here, but here they're becoming farther, so field is becoming weaker, and it doesn't have specific measurement. You have to just be consistent in your drawings, which means that fields that are twice as strong must be represented by twice as many field lines per unit area. The second thing is the surface penetration is a two-way street. Once the direction of surface normal and has been established, field line components parallel to that direction give a positive flux, while components in the opposite direction and type parallel to and give a negative flux. Thus, a surface penetrated by 5 field lines in one direction, say from top to the bottom, and 5 field lines in the opposite direction, has zero flux. For example, if we have a field this way and the other field this way, they're just going to cancel each other, give us zero flux, because the contribution from the two groups of field lines cancel. So one has a positive direction, for example, if n was in this way, and the other one has a negative direction opposite to n. So positive, negative will cancel. So you should think of electric flux as a net number of field lines penetrating the surface, with direction of penetration taking into account. If you give some thought to this last point, you may come to an important conclusion about closed surfaces. Consider 3 boxes shown in figure 1.8. So this is figure 1.8. The box in figure 1.8a is penetrated only by electric field lines that originate and terminate outside the box. Thus, every field line that enters must leave, and the flux through the box must be zero. If you give some thought to this last point, you may come to an important conclusion about closed surfaces. Consider the 3 boxes shown in figure 1.8, which is this figure. The box in figure 1.8a is penetrated only by electric field lines that originate and terminate outside the box. Thus, every field line that enters must leave, and the flux to its box must be zero. Here we can see that flux is entering, and here it's leaving, so the total inside the box must be zero. Remembering that the unit normal for closed surfaces points away from the enclosed volume, you can see that inward flux lines entering the box is negative. Since electric field dot product, the unit normal must be negative when the angle between E and N is greater than 90. This is precisely cancelled by the outward flux lines exiting the box, which is positive. Since electric field dot product N is positive when the angle between E and N is less than 90. So it's telling us here that one side will have a positive direction and the other side will have a negative one. This is the direction of the flux, and this is the direction of the unit normal. So it just points out of the surface. So this one will have a negative direction and this one will have a positive direction, and will cancel each other. And without the mathematical equations, we could just see that it enters and leaves. So nothing actually stays inside the box. Now consider the box in figure 1.8b, this figure. The surface of this box are penetrated not only by the field lines originating outside the box, but also by a group of field lines that originate within the box. So that means there is some sort of source inside the box. In this case, the net number of field lines is clearly not zero, since the positive flux of the lines that originate inside the box is not compensated by any incoming negative flux. Thus, you can say with certainty that if a flux through any closed surface is positive, the surface must contain a source of field lines. So here, when it just entered and left, there's no source here. The source was here and it terminated outside the source, and termination was outside. But the other one, there was flux starting at the surface and leaving it. That means there's a source in here that created those flux lines. Finally, consider the box in figure 1.8c. It's the opposite of figure B. The lines are being terminated inside the box. That means we have a negative charge. So let's read. Finally, consider the box in figure 1.8c. In this case, some of the field lines terminate within the box. These lines provide a negative flux at the surface through which they enter, and since they don't exit the box, their contribution to the net flux is not compensated by any positive flux. Clearly, if the flux through a closed surface is negative, that surface must contain a sink of field lines. So a sink, that means a place where the field lines will just terminate. So we could say it's a sink or a drain. Or now recall the first rule of thumb for drawing charge-induced electric field lines. They must originate on positive charge and terminate on negative charges. So the point from which the field lines diverge in figure 1.8b marks the location of some amount of positive charge, and the point to which the field lines converge in figure 1.8c indicates the existence of a negative charge at that location. If the amount of charge at these locations were greater, there would be more field lines beginning or ending on these points, and the flux through the surface would be greater. And if there were equal amounts of positive and negative charges within one of these boxes, the positive outward flux produced by the positive charge would exactly cancel the negative inward flux produced by the negative charge. So if we had a box and it has a positive charge that has, for example, 3 lines coming out of it, and there's another charge, negative, that has 3 lines coming into it. So those 3 will cancel those 3, and the net flux will be 0. You should now see the physical reasoning behind Gauss's law. The electric flux passing through any closed surface, that is, the number of electric field lines penetrating that surface, must be proportional to the total charge. So now it makes sense. So the number of lines is proportional to the charge actually in it. So now Gauss's law is starting to make sense. Before putting this concept to use, you should take a look at the right side of Gauss's law. So Gauss's law had an integration part of electric field dot product N over closed surface, and the other side had Q enclosed over the permittivity of free space. That's why it was concerned by enclosed charges. Now let's talk about the enclosed charge. If you understand the concept of flux as described in the previous section, it should be clear why the right side of Gauss's law involves only the enclosed charge, that is the charge within the closed surface over which the flux is determined. Simply put, it is because any charge located outside the surface produces an equal amount of inward negative flux and outward positive flux, so the net contribution to the flux through the surface must be 0. So anything outside here will have a negative contribution. Only what matters is the charge is enclosed in the surface. How can you determine the charge enclosed by a surface? In some problems, you're free to choose a surface that surrounds a known amount of charge, as situation shown in figure 1.9. So this is figure 1.9. In each of these cases, the total charge within selected surface can be easily determined from geometric considerations. For problems involving groups of discrete charges enclosed by surfaces of any shape, finding the total charge is simply a matter of adding the individual charges. So the total enclosed charge is just using the summation. A small number of discrete charges may appear in physics and engineering problems. In the real world, we are far more likely to encounter charged objects containing billions of charge carriers. We will not be just adding them together. They're not discrete, so it's not like 2 or 3 charges that we could sum. It's billions of charges on the surface or in a volume. In such cases, counting the individual charges is not practical, but you can determine the total charge if you know the charge density. So, for example, if we know there are a specific number of charges per specific area, we could just integrate over that area to find the total number of charges on the total area. Charge density may be specified in 1, 2, or 3 dimensions. So here are just some examples. And now charges could be on a line, on a surface, in a volume. Okay, it could tell us a specific number of charges, and for example, charges per 1 meter, or there are specific charges on meter square or volume charge per meter cube. If these quantities are constant over the length, area, or volume under consideration, finding enclosed charge requires only a single multiplication. So to find the total charge on a line, we'll just multiply how many charges per meter times the total length, and we'll do the same for all, like whether it's area or volume. You're also likely to encounter situations in which the charge density is not constant over the line. So for example, there may be a lot of charges in here, a few charges in there, 2 charges in here. In such cases, the integration techniques described in surface integral section of the chapter must be used. So first, if it was over a surface, we'll just do the surface integral described above, and we'll do the same if it was on a line. We'll do line integral and volume integration. We'll just integrate to find the total charge on a volume. You should note that enclosed charge in Gauss's law for electric fields is the total charge, including both free and bound charge. You can read about bound charge in the next section, and you'll find a version of Gauss's law that depends only on free charge in the appendix. Once you've determined the charge enclosed by a surface of any size and shape, it's very easy to find the flux through that surface. Simply divide the enclosed charge by the permittivity of free space, the physical meaning of that parameter described in the next section. Finally, this is the last thing we have in Gauss's law. The constant of proportionality between the electric flux on the left side of Gauss's law and the enclosed charge on the right side is permittivity of free space. The permittivity of material determines its response to an applied electric field. In non-conducting materials, called insulators or dielectric, charges do not move freely, but may be slightly displaced from their equilibrium positions. The relevant permittivity in Gauss's law for electric fields is the permittivity of free space, or vacuum permittivity, which is why it carries the subscript 0. The value of the vacuum permittivity in SI units is approximately this number, coulombs per voltmeter. You will sometimes see the units of permittivity given as farads per meter, or more fundamentally, this unit, a more precise value for the permittivity of free space is this, but mostly we'll just estimate it to this value. Does the presence of this quantity mean that this form of Gauss's law is only valid in vacuum? No, Gauss's law, as written in this chapter, is general and applies to electric fields within dielectrics as well as those in free space, provided that it account for all enclosed charge, including charges that are bound to atoms of the material. The effect of bound charges can be understood by considering what happens when a dielectric is placed in an external electric field. Inside the dielectric material, the amplitude of the total electric field is generally less than the amplitude of the applied field. The reason for this is that dielectrics become polarized. We'll see what does that mean. When placed in electric field, which means the positive and negative charges are displaced from their original positions. So if we had a positive and negative like that, if an electric field is applied, maybe the positive will go away a little bit and the negative will go away a little bit, but still it didn't leave the material. And since positive charges are displaced in one direction parallel to the applied electric field, and the negative charges displayed in the opposite direction anti-parallel to the applied electric field, these displaced charges give rise to their own electric field that opposes the external field, as shown in 1.10. This makes the net field within the dielectric less than the external field. It is the ability of dielectric material to reduce the amplitude of an electric field that leads to their most common application, increasing the capacitance and maximum operating voltage of capacitors. So capacitors rely on this concept. As you might recall, the capacitance ability to store charge of a parallel plate capacitor, where A is the plate area, D is the plate separation, and E is the permittivity of the material between the plates. So this one is not for the free space. For example, if we have two plates like that and we want to calculate the capacitance and there is a specific material between them in the middle, this E will be the permittivity of this material. High permittivity material can provide increased capacitance without requiring larger plate area or decreasing plate spacing. The permittivity of a dielectric is often expressed as the relative permittivity, which is the factor by which the material's permittivity exceeds that of free space. High permittivity materials can provide increased capacitance without requiring larger plate area or decreased plate spacing. High permittivity materials can provide increased capacitance without requiring larger plate area or decreased plate spacing. The permittivity of a dielectric is often expressed as the relative permittivity, which is the factor by which the material's permittivity exceeds that of free space. So the relative permittivity is just a ratio between the material's permittivity and the free space's permittivity. Some texts refer to relative permittivity as dielectric constant, although the variation in permittivity with frequency suggests that the word constant is better used elsewhere. The relative permittivity of ice, for example, changes approximately 81 at frequencies below 1000 Hz to less than 5 at frequencies above megahertz. Most often, it's the low frequency value of permittivity that is called the dielectric constant. One more note about permittivity is you'll see in chapter 5, the permittivity of a medium is a fundamental parameter in determining speed in which an electromagnetic wave propagates through the medium. So this is the final form of Gauss's law. A good test of your understanding of an equation like Gauss's law is whether you're able to solve problems by applying it to relevant situations. At this point, you should be convinced that Gauss's law relates the electric flux through a closed surface to the charge enclosed by that surface. Here are some examples of what you can actually do with that information. So we'll see one example, and there are 4 more examples you could see by yourselves. Given a charge distribution, find the flux through a closed surface surrounding that charge. 5-point charges are enclosed in cylindrical surface. If the value of the charges are those values, find the total flux through S. So here actually the charges are discrete. Let's see the equation first. The flux is the integral form, the surface integral of that Q enclosed over permittivity of free space. For discrete charges, you know that the total charge is just the sum of the individual charges. We'll just add them all together to find Q enclosed, and then to find the flux, we'll just divide by the permittivity. This is the total flux through any closed surface surrounding this group of charges. So for example, if we had a surface like that, the total flux through the surface will just be this number, as long as we didn't include more charges when we made this surface. So this was the first video, the first part of this book. So let's see what we read. So there are 4 Maxwell's equation, and in this video we looked at the integral part of Gauss's law for electric fields. In further videos, we'll complete reading the book and we'll learn about Maxwell's equations and the applications. In even further videos, we may go and explore electromagnetic fields from other books. Thank you for watching. Leave a comment for better suggestions. It would be really appreciated, and subscribe. See you in the next video.